Okay, so I've given you this protocol. I've given you this protocol. Now the remarkable thing, this protocol is completely practical, but it's hard to prove rigorously. This protocol is easier to prove rigorously, but you need a quantum computer to implement it. So the amazing thing is that these protocols are actually secretly exactly the same protocol. So if this is secure, this is secure. So let's go back and start fiddling with this protocol to make it look like this protocol. So what is going on? Is this chalk actually white? Yeah. Okay. So remember what the CSS code was. CSS code, you C1 and C2. No, I call them CA and CB. CA is contained in CB. Okay, and now A and B are problems because these are completely unrelated to Alice and Bob. But so maybe we should go back to rename these C1 and C2 to be less confusing for this lecture. A code word is x plus C1 is equal to 1 over the normalization factor times the sum over all C in C1 x plus C, where this is bitwise addition, mod 2. For x in C2. So Alice sends Bob one of root C1 some x plus C1. Okay. For the code word, actually, maybe we should do something first. So Alice and Bob share n perfect EPR pairs. Alice prepares them, encodes them, and sends them over, and then Bob decodes it and measures it. It really doesn't matter if Alice measures it, and Alice is going to measure her perfect EPR pairs too. It really doesn't matter whether Alice measures them before she encodes them or she encodes them before she measures them. Because, once Alice, where is this? Yeah, so Alice has encoded these EPR pairs. And she's going to measure them after she's sent them all to Bob. But measurement commutes with doing anything on the other half of the EPR pairs, so she might as well just measure them before she sends them all to Bob. And now what is she doing? She's taking a random state and she's encoding it in a CSS code. So Alice is taking a random state, is actually just a random x in a random coset of C1 in C2. So here is where maybe I should have introduced the mathematical notation for cosets, but I'll see if I can get away with that without it. So she takes a random coset of C1 and C2 and encodes it. Well, and she also sends Bob. let's do this in 0, 1, plus, minus as test bits. And she sends these randomly, and she also, what? Yeah. And then after that, she tells Bob, after Bob has put everything in quantum memory, she tells Bob which of these are test qubits and which of them are real qubits, or encoded qubits. And then Bob decodes, and he gets the bits that Alice sent. So what? Yeah, this gives us the bit error rate, and this gives us the phase error rate. And those two rates are enough to tell us whether the quantum error correcting code is good enough to preserve information against the noisy channel. So what do we do now? Well, note that 0 plus 1 equals 1/2 plus minus equals I/2. So these are completely mixed quantum states. So the test qubits are in a completely mixed quantum state, which means Eve can observe any information from looking at them. But if you look at the code word is not in a completely mixed quantum state. So maybe Eve could get some information by looking at the code word. So let's do something different. Let's turn the code word into a completely mixed quantum state. So Alice sends Bob a shifted code word. I'm going to root C minus 1 to the x, okay, minus 1 to the s dot c x plus c plus t. So why is this shifted code word? Well, first, we're shifting by t here. And second, remember the quantum error correcting codes. If you took the Hadamard of them, they turned into another quantum error correcting code with C2 dual contained in C1 dual. And if you do that, you find a shift in the Hadamarded code corresponds to a minus 1 to the s dot c in the original code. And if I have time at the end, I will go through this calculation, but I don't think I'm going to have time at the end, so just trust me on this. You can do it yourself. In fact, that might be a good question to put on the homework if I don't get to it. Well, would that, actually, I don't think we can do that with the, well, maybe we can be clever of that and do that with the edX format, but we'll have to be clever. I'll think about it. Anyway, so this is the shifted code word. And with a shifted code word, both phase shift and a bit shift, average over ST is the completely mixed state. Mixed state. And I should explain this part at least. Actually, I think I only really need to explain the -1 to the S dot C part. Okay, so summation C in C1, X plus C. The density matrix looks like is 1 over C1, 1, 1, 1, 0, 0. So you get ones wherever you have an X plus C, wherever you have X plus C as the row and X plus C as the columns, and zeros everywhere else. So just pretend that the zeros are there. So now you change that to 1 over C dot 1 to the 1/2 summation C in C1 minus 1 to the C X plus C. What happens is you have some columns and some rows where you multiply them by -1. And in fact, it's the same rows as columns. So what happens when you do that? Well, you get a -1 here, and a -1 here, and here, and here. So the diagonal elements all stay 1s, and the off-diagonal elements, some of them turn to -1s. And when you average it over all, oh, this is supposed to be S dot C. When you average that over all S, the off-diagonal elements are equally likely to be +1 and -1, so they cancel out, and the density matrix you get when you average over all the S's is 0, 0. Just that. And now you average over all the T's, that covers all the diagonal elements equally often, and so you get the completely mixed state. So this average of this is over S and T is a completely mixed state. So here we have a new protocol. Alice sends Bob a shifted code word interspersed with test qubits, and Bob decodes it. Well, and Bob puts it in memory, and then Alice sends Bob S and T, and Bob decodes it. Okay. So we'll change the last thing, and codes in shifted CSS code characterized by S and T, and then Alice sends Bob ST and everything about the test qubits. Bob measures noise rate and decodes. And here, Alice actually doesn't have to prepare n EPR pairs. She prepares n random bits, which we showed was equivalent to preparing n EPR pairs. because it didn't matter whether she measured her half of the ETR pairs first or second. So Alice prepares n random bits, encodes in a shifted CSS code, intersperts m test bits in random state, sends the encoded pairs and the test qubits to Bob. Bob stores everything in quantum memory, and then Alice and Bob sends Bob the ST. Bob measures the noise rate and decodes.